In today's video, we're going to look at section 2.3, arithmetic operations on matrices. In this section, we're just going to discuss exactly what is a matrix, and then how can we put these matrices together. So how can we add them, how can we subtract them, and then eventually we're going to look at multiplying. But first, I want to look at some fundamental things and properties of matrices, just so that we are all on the same page before we go ahead and do this. So what exactly is a matrix? We've been dealing with them in the last couple sections, but how do we define a matrix? A matrix is literally just a rectangular array of numbers. Okay. It doesn't matter how many rows you've got, how many columns you've got, as long as every single entry actually has a value in it within those rows and columns. It can be whatever size that you like, as long as it is rectangular. As I said, we can add these together, we can subtract them from one another, and we can multiply them together. And we're going to look at each of those functions. And eventually we will also look at some real world examples of where these things are used. Just as general notation, whenever we refer to the size of a matrix, it's always given in terms of row by column. So you're going to get something, when you look at the size, it's going to look like A times B. Okay, we actually call this A by B. Okay, so for example, if we have this matrix, I'm just going to make up a random matrix here. This matrix has 3 rows and 2 columns, so we call it a 3 by 2 matrix, and that's how we write it. Okay, if you had 2 rows and 3 columns, it would be a 2 by 3 matrix, so it's always the number of rows by the number of columns, so the rows always go first. So whenever you see that notation, that's what it means. If a matrix only has one row, it's called a row matrix. So a row matrix is literally just a matrix with one row. So an example of that would be something like this. Don't put commas or anything between each of the entries, especially when you've got a row matrix. It's kind of, people tend to try to do that to make it look like a pairing or something weird like that. Don't do that. Just make it, each entry is its own thing, and don't put any commas between them. But this is called a row matrix. You can have as many columns as you like. You can have one or however many. It doesn't matter, but this is a row matrix. Column matrix similarly has one column. So an example of that would be something like this. Okay, so it just has one column, however many rows. If you have a matrix that has the same number of rows and columns, then it is called a square matrix. So a square matrix has the same number of rows and columns. So an example of that would be a 3 by 3 matrix. Has 3 rows and 3 columns, same amount of rows as columns, and it could look something like this. That would be a square matrix. This is more of a notation thing. So for example, if I go back to my last matrix that I wrote out, this 3 by 3 matrix here, I'm going to write this out. I'm going to call this matrix A. General notation, whenever you refer to a matrix, you always use a capital letter. Okay, so we're going to call this capital A. It's going to be what this matrix is called. And then we also need to deal with subscripts, because let's say I am referring to this entry here. Okay, this 8. I would refer to this as A3, 2. Okay, A3, 2 is equal to 8. I use the lowercase version of whatever letter I've used to denote my matrix. And then it is the 3, 2 entry. It is in the third row and the second column. So it is the 3, 2 entry. If, for example, I was looking at this 3 here, that would be A1, 3. Okay. Again, I've used that lowercase a, and then it is in the first row and the third column. So you always do row, comma, column. Okay. If we want two matrices to be equal, so if A equals B, you've got two conditions here. Number one, the matrices have to be the same size. And number two, the corresponding entries also have to be equal. Okay, so every single entry has to be the same as the entry that is in the other matrix. So for the above matrix that we have here, B would literally have to be the exact same matrix. So the exact same size, and each entry is in the exact same position. So I have a 1 in my first position here, in my 1, 1 position. My 1, 2 position is a 2, etc. So if A equals B, number one, they have to have the same size. And the second thing is that they have to have equal corresponding entries. So they must look exactly the same. Now we're going to look at adding two matrices together. So if we add two matrices together, they have to be the same size. Why is that important? Well, we add the corresponding entries to each matrix. So when we do this, let's say our example, I'm going to do two different 3 by 2 matrices. So I've got 1, 2, 4, -1, 3, -9, plus -2, 6, 1, 1, -4, 7. So I'm adding these two matrices together. They have to be the same size because when we add matrices, we just add their corresponding entries. So my 1, 1 entry, this first entry in my resulting matrix, is just going to be this 1, 1 entry plus this 1, 1 entry. So 1 plus -2 gives me -1. Then 2 plus 6 gives me 8. 4 plus 1 gives me 5. -1 plus 1 gives me 0. 3 plus -4 gives me -1. And -9 plus 7 gives me -2. Okay. So this is how we add matrices together. You literally just add their corresponding entries. Same deal goes for if you're subtracting matrices. So when you subtract matrices, you just subtract the corresponding entries. Same deal goes for when you were adding them. You have to have matrices of the same size or this doesn't work. So if I took my last example, but this time I subtracted the two matrices, I just subtract my corresponding entries. So 1 minus -2 is going to be 1 plus 2, which is 3. 2 minus 6 gives me -4. 4 minus 1 is 3. -1 minus 1 is -2. 3 minus -4 is 7. And -9 minus 7 is -16. Okay, so it works exactly the same as adding matrices. We have to make sure that the matrices are of the same size, and then we just add or subtract the corresponding entries accordingly. The other thing that you can do is multiplying a matrix by a scalar. That means that I'm just multiplying a matrix by some constant value. Okay. So when multiplying a matrix by a scalar, you multiply every entry in that matrix by that scalar. Make sure that you do that to every entry, because people tend to just do random mathematical errors with this and miss an entry or something. So make sure, particularly in an exam situation, that you multiply every entry in that matrix by that scalar. It's exactly the same as when we were doing the Gauss-Jordan method, where we were multiplying a row by a scalar. Make sure that you would multiply every entry in that row by that scalar. Same deal goes here. You are just going to multiply every entry in the entire matrix by that scalar. So our example for multiplying a matrix by a scalar, it would look something like this. So I have 5 multiplied by this matrix, so I multiply every entry in my matrix by 5. Okay, so how do I do this on my calculator? The first thing you need to do is to go into the matrix menu. So you're going to go to second and matrix. I've already put these matrices in, but I'll show you how I did it. You go across to edit. We did this before when we looked at the reduced row echelon form for our Gauss-Jordan elimination. You go across to edit and you click on your first matrix, A. Now in our example, A was a 3 by 2 matrix. So I've just clicked 3 by 2. And then you can edit each of the entries in your matrix. Just go along, you can go up and down and side to side to change each of the entries in the matrix. Once you have done that, you actually have to come out of the matrix menu and then go back in. So you're going to go second, quit, and then you're going to come back in. So second and the matrix menu. Go across to edit, and now you can do matrix B. It's annoying that you have to come out and go back into that matrix menu, but otherwise it tries to give you a matrix inside a matrix and it gets messy. So whenever you do this, for each matrix, always go back into the matrix menu to edit a new matrix. So I've put my matrix B in exactly as it was in our example. Then you come out of there. Now in my first problem, I added the matrices, then I subtracted them, and then I multiplied by a scalar. So to do this, I go into my matrix menu and I call the matrix A. So you stay on this first menu of names and you just click A. And then I added my matrix B. So I go down to B, click enter. Okay, so this time I'm calling the matrices. I'm not editing them, I'm calling them. So stay in that names menu and just click on the matrix that you want to use. So I did A plus B. If I click enter, it gives me the exact same matrix that I got when doing this by hand. To subtract them, you do the same thing. So I go into my matrix menu, I call matrix A minus matrix B, gives me the same matrix that I had when I worked this out by hand. And finally, to multiply by a scalar, you literally do it like we wrote it. So I had 5 times my matrix A. So 5, and then I'll call my matrix A. And I get that matrix. So you can literally just do 5 and then A. You don't have to do multiply or anything. Just do 5A. Okay. So whenever you do this, use that matrix menu, and remember, I know it's annoying, but you do have to come out of the matrix menu each time you want to input a new matrix. So we have looked at scalar multiplication of these matrices. So we've seen how we can multiply a scalar and a matrix together. But now I want to see what happens if I multiply 2 matrices together. In order to define how we're going to do this, because I will tell you now it's not just element by element like we did with addition and subtraction. To define it, we're going to use something called the dot product as our base for what we're going to do. And this is actually something that comes up in calculus when you effectively multiply 2 vectors together. So first I'm going to look at the dot product. The dot product defines how we effectively multiply a row matrix by a column matrix, okay? Or a row vector by a column vector if we were looking at this in calculus. So I'm going to start with this and then I'm going to extend it for our matrices. So a dot product, let's say we've got this row matrix, I'm going to call it A, and its entries, it can have n entries, so I've got n columns, but just one row. And I'm going to call my matrix B this column. Okay, so A has one row, B has one column. The dot product is defined such that you go along the row and down the column and you multiply each of the corresponding entries together and then add them all up. So it would look like this. Okay. It's just a scalar. It's just a number that you get out at the end of this. A big thing here, and this was something we talked about when we did addition and subtraction of matrices, is the size of the matrix. We have to be aware of the size. We have here n columns, and in B we have n rows. That means that we have the same number of corresponding elements in each of our matrices that we can multiply together and then add up. Okay, if A only had 4 entries but B had 5, then we would end up with this random entry at the end that couldn't multiply anything in A, and therefore it would mess up. So when we do this, we have to make sure that both A and B have the same number of entries. So this is how the dot product is defined. So for example, if I did 1, 2, 3 dotted with 4, 5, 6, okay, I would get 1 times 4 would give me 4, plus 2 times 5 would give me 10, plus 3 times 6 is 18, which gives me 32. Okay, it's just a number. How do I extend this dot product I did to matrices? I'm going to do this via an example so that you can see what happens and some properties that we have to have for our matrices in order to be able to multiply them. So the example that I'm going to use is going to be 2, 1, 0, 1, 3, 4, multiplied by 1, 5, 2, 7. Okay. and I'm going to multiply these together. When we used the dot product, so we did row multiplied by column. So we then just multiplied each of the corresponding entries in the row and column together, added them all up. I'm going to do the same thing here, and remember how our entries for a matrix worked. Okay. For example, if I had a resulting matrix, we're going to call our resulting matrix of multiplying these two together A. My first entry that was in my first row, first column was A11. The entry that was in the first row, second column was A12. The entry that was in the second row but first column was A21, etc. And you filled it out like this. This is going to be very useful when we multiply these together. Okay. If I go ahead in my matrix, I'm going to multiply my first row by my first column. Okay, I'm going to take the dot product of these two. So I get 2 multiplied by 1 plus 1 multiplied by 5. So that's 2 plus 5, which is 7. Okay. I got that value by multiplying my first row by my first column. Okay. That tells me that that entry is going to go in the 1, 1 entry. That value came from multiplying row 1 by column 1. So my 1, 1 entry in my resulting matrix is 7. I took the dot product of the first row in my first matrix by the first column in my second matrix. Now I'm going to take the dot product of my first row and my second column. That would be the A12 entry. Okay, I've done the first row in my first matrix times or dot product with the second column in my second matrix. So this is going to be this entry in my matrix. So it's going to be 2 times 2 plus 1 times 7 should give me 11. So my A12 entry is going to be 11. Okay. I don't have any more columns in my second matrix. I've exhausted my second matrix because I've done this row multiplied or dot product with every column that I can in my second matrix. So I now move on to my next row. Okay, I'm going to do the same thing again. I'm going to do this row, dot product with this column. That should give me my A21 entry because I'm multiplying or dot product my second row of my first matrix and my first column of my second matrix. So this should be the A21 entry. So I'm going to have 0 times 1, 0 plus 1 times 5. My A21 entry is 5. And then I do row dotted with column should give me 0 plus 7 is 7. Again, I've exhausted all the columns in my second matrix. So I now move on to my next row and I take the dot product of that row with each of my columns. So this time I will get the 3, 1 entry and the 3, 2 entry. So I'm going to have 3 plus 20 will give me 23 and 6 plus 28 will give me 34. And that is my matrix. So all you are doing when you multiply two matrices, you do rows in the first matrix, dot product with columns in the second matrix. Don't worry about any columns in the first matrix or rows in the second matrix. It's always rows in the first one and columns in the second one. And you can figure out which entry you're working with in your resulting matrix by figuring out, okay, which row am I on in my first matrix and which column am I on in my second matrix. So for example, when I did this row, my second row and my first column dot product together, that would be my 2, 1 entry in my resulting matrix. So this matrix here is found by multiplying this matrix by this matrix. Now, because we are not multiplying in what I would think of as a standard way, like we did with addition and subtraction. We're not doing it entry-wise. We're not just going, okay, I'm doing my first entry in my first matrix times my first entry in my second matrix, and that gives me that entry. No, we're dealing with rows and columns here. Because of that, the order that these matrices are given in matters. So I have to make sure that I can actually multiply these matrices in the order in which they are given. Good example is by taking these two matrices but flipping them around. So this time my first matrix is going to be this matrix, 1, 2, 5, 7. And my second matrix is going to be this matrix here, 2, 1, 0, 1, 3, 4. And I'm going to see if I can multiply these together. So again, we do this by taking the dot product of rows in my first matrix and columns in my second matrix. So I would do my first entry in my resulting matrix would be the dot product of this row and this column. Well, I would get 1 multiplied by 2 is 2, 2 multiplied by 0 is 0, but I still have another entry in this column that can't multiply anything because I don't have another column in my first matrix for it to multiply another entry. So therefore, I cannot multiply these matrices this way around. I can only multiply them when this matrix was first and this matrix was second because of this dimension argument. So in reality, this multiplication is actually undefined. Because I cannot take the dot product of rows in my first matrix and columns in my second matrix. When you get an example without having to go through any kind of multiplication or anything to figure out if it was defined or not, you can actually just look at the size of the matrices and figure it out. If I come back to this example where this multiplication was defined, okay, this first matrix, it had 3 rows and 2 columns. It was a 3 by 2 matrix. My matrix here was a 2 by 2 matrix, 2 rows, 2 columns. In order for this multiplication to actually be defined and to actually get an answer out, you should have these two numbers here match. So if I'm multiplying a 3 by 2 matrix by a 2 by 2 matrix, the two inside numbers should match. Okay, so this number and this number should match. If we did this example here where we flip them around, I've got a 2 by 2 matrix multiplied by a 3 by 2. These two numbers do not match. They are now different. The two interior numbers are different. Therefore, this multiplication is undefined. The next thing that I want to look at pulls us back to looking at these systems of equations and where we use matrices in order to solve our systems of equations. I quickly want to show you another way of writing these systems. So let's say that we had the following system of equations. I'm just going to use 2 here, just as it's an easier problem that way. Okay. Let's say that we have this random system. I can rewrite this, like we said, as this matrix that we can use to do the Gauss-Jordan elimination method on, and I can put it into reduced row echelon form, and I can go ahead and find my solution. When we wrote that matrix down, it looked like this. And we said that the left-hand side of that matrix looked at the coefficients of x and y for our system, and then the right hand side looked at what it equaled to, what the constants were on the right hand side of the equations. The reason that we write it like this is because it actually links us back to this matrix multiplication argument. I can rewrite this system in the following form. Why is this? Well, let's go back to how we multiply matrices. I do row times column, so I do the dot product. So that will give me 2 times x plus 4 times y. And because I've done the first row multiplied by that first column, it gives me the 1 entry in my resulting matrix. Do the same thing. I've exhausted columns here, so now I don't have anything else to multiply this row by. So I go to my next row. I do row times column, do the dot product. So that gives me 3x minus 7y, and I've done second row times first column, gives me the 1 entry in my resulting matrix. Okay, this is where it's really useful to remember which row and column you are multiplying, because then it tells you what your resulting matrix is going to look like. Is it going to look like a row? Is it going to look like a column, etc.? Because here we did second row times first column, giving me a 2-1 entry, not a 1-2 entry. So remember, that's how it would look, and therefore we have this column matrix. So what we have effectively done when we put our matrix into this form, we've condensed this argument here. Okay, we've basically taken the x and the y out, which is what we said when we wrote it that way. But the question is, why can we write it that way? And the reason is because this thing here is called a coefficient matrix, where if I multiply that by this vector, this column matrix x, y, it equals this column matrix that I have on the right hand side. So just as a heads up in terms of wording and notation, etc., when we write this, we tend to say a times x equals b. So this matrix here we always denote as a capital A. This vector of our variables, okay, it's a column matrix or a vector, we denote as x, capital X. And this column matrix here, or a vector, we denote as B. Okay, so you have matrix, which we call a coefficient matrix, is another name for it. We denote that by A, and then our column matrix of variables is just X, and then, like I said, that right-hand side we denote as B. The last thing that I want to talk about in this video is something called the identity matrix. And this identity matrix is a square matrix that when I multiply it by another matrix, I end up with the same matrix. We denote it as I. So let's take a particular matrix. I'll make up a random matrix here. Okay, I've got this random square matrix. I'm going to multiply this by this particular matrix, and I'll show you what happens, and then we'll extend this to larger arguments. If I take the multiplication of these two matrices, again you do row times column, row times column, row times column, row times column. Okay, so I get 2 times 1 is 2, plus 1 times 0, that leaves me with 2. Then I get 2 times 0, 0 plus 1 times 1 is 1. Then my 1 entry is going to be 4 times 1 plus 6 times 0. That's going to give me 4. And then my last term is going to be 4 times 0 plus 6 times 1 is 6. I end up with the same matrix that I started with. Okay? So what does this matrix do? The identity matrix just gives you the same matrix back whenever you multiply it by another matrix. It doesn't matter, apart from the size of the matrix, it doesn't matter which side you would have multiplied this on. I could actually multiply it on either side and get the same thing, which isn't in general true when you multiply matrices, because when you think about it, you would be multiplying different rows and columns in general, so you're going to end up with a different answer if you flip this around. Or the answer actually may be undefined in some cases due to the sizing of the matrix. But with an identity matrix, as long as your dimensions match up, meaning that those middle two numbers that we talked about match, it doesn't matter which way around you multiply this, you're going to end up with the same answer. And that is true here. If you were to calculate this again, you still end up with 2, 1, 4, 6. Okay. So what does the identity matrix look like? The identity matrix that we denoted as a capital I is just a 1 on the diagonal entries and zeros elsewhere. Okay, so for example, a 3 by 3, there's different notations for it. You can see it as I3, sometimes it's denoted as I33. There's different notations for it. But that would be a 3 by 3. They're always square. Let's make that a note. They are always square. Okay. And it is a 3 by 3, what we call diagonal matrix, with 1s on the diagonal, zeros elsewhere. Very similar to those matrices that we were looking at when we did that Gauss-Jordan elimination back in 2.1 with unique solutions to the system. Our left-hand side looked very much like this. Okay, this is called the identity matrix. Always square. You tend to find that they will tell you how big the matrix is with this little subscript here. Sometimes they don't, and you have to figure it out from the problem, or they tell you it's a 3 by 3 identity matrix, etc. But it will always be square with 1s on the diagonal and zeros on the off diagonal. And all it does is when you multiply it by another matrix, it's going to give you the same matrix back. Okay, so if you think about it in terms of scalars, it's effectively a 1. Okay, if I multiply any number by 1, I get the same number back. Okay, so that's effectively what this does, but in matrix form. As I said, please be aware of sizing and dimensions of these matrices, especially when you're multiplying by an identity matrix. If I took this matrix here and multiplied it by a 2 by 2 identity matrix, okay, this would work out in terms of my sizing, because I have a 3 by 2 for my dimensions of my first matrix and a 2 by 2 for the dimensions of my identity matrix. These two numbers match, and the size of the matrix that I get out is always the exterior numbers. It's a 3 by 2. Okay, so that's fine. But if I would have multiplied these the other way around, this doesn't match up, because I have 2 entries here, dot product with 3 entries here. That doesn't work out, because when we look at this, my interior numbers don't match. Okay, the 2 and the 3 don't match. Therefore, this is undefined. In order to make this defined, to get this matrix back out as we said the identity matrix does when you use it in multiplication, you would have to have a 3 by 3 here. Okay, so it would have to look like this, because then I have a 3 by 3, my interior numbers match, and the exterior numbers are the dimensions of the matrix that I would get out, and then I would get this matrix back by multiplying it by this 3 by 3 identity matrix. So you really need to look at the dimensions of the matrix in order to see what size of an identity you would have to multiply it by to get the same thing back. Same goes with any kind of matrix here. Whenever we do multiplication of matrices, like I've said the whole way through, we have to make sure that our dimensions are correct in order for this multiplication to even be defined. Okay, so please make a note of that when you are looking at multiplying matrices so that you don't come across a problem. Okay, so how do we do this matrix multiplication on the calculator? First thing you want to do is to go back into your matrix menu, and you're going to input what your matrices are. So I've already done this. So matrix A, if you're going to edit a matrix A, I've put this 3 by 2 matrix. It's the same one from our example for matrix multiplication. So I've got 2, 1, 0, 1, 3, 4. And remember, it's a 3 by 2 matrix, 3 rows, 2 columns. So you input your matrix A, come out of the matrix menu, and then go back in, go to edit, and then put in your matrix B. This one was a 2 by 2, 1, 2, 5, 7. So I've input that matrix as well. I'm going to come out of the matrix menu, and now I'm going to try and do A multiplied by B and B multiplied by A. So if I go to second and matrix, I'm going to call matrix A, second matrix, call my matrix B. You don't need to do multiply between them, just do A, B. And it should give you that solution, the same one that we had when we did this by hand. Like we said when we did this example, B times A was undefined. So I can again do that in my calculator. So remember, the order in which we multiply matters, because not only can it change the solution because we're now multiplying different rows and columns, it can actually be undefined, which was the case in this example. So B times A, we get this error that says dimension mismatch. We knew that that was the case. So this is always a great check. Whenever you get a problem like this, if you think it's undefined, you can also put it into the calculator. And it's also a good check for any of your matrix multiplication problems.